I can say that, oh, sorry. Yeah. I can say that my research is to understand quantum spacetime. So now we have quantum spacetime, then that includes two technical terms. So let me explain step by step. So first, what is spacetime? So I think you can imagine the universe, the gigantic one, at the given time. So if you, sorry. So if you pile up the universe at a given time in a time direction, then you can construct the whole space-time. So space-time is a sort of flip book, gigantic flip book of the universe, in that sense. So if we write down some, if we draw some picture of the universe, you can see like that. So this is the, well, the picture of space-time. So, but I think the space-time can be seen as a sort of vessel, which is not empty, as you know. So there are many stars and galaxies and black holes and other types of energy. I don't know, but so if I draw like this, you may think that this sort of vessel, a space-time, is a fixed object. We cannot change the shape, but it is not the case actually. According to the Einstein's general theory of relativity, the space-time is a sort of dynamical entity. Its shape can change depending on the matters or some energies in the space-time. So actually, this dynamics can be well described by general relativity by Einstein. And then next, quantum. So what is quantum? The quantum comes from the theory that can describe the physics at the very short scale, very small scales. Quantum mechanics. Okay. And at the very small scales, for instance, the motion of particles cannot be predicted precisely, which is quite different from what we have learned from, say, ordinary life. From our ordinary experience, we can say predict the correct particle motion by just solving the equations of motion. However, we cannot at the very small scales. And actually, kind of very weird thing happens in a very small scales. And that kind of weird physics can be well described by the quantum mechanics. Okay. And so then, what is a quantum spacetime? So I think I can say that quantum spacetime is the spacetime at the very, very small scales. So if you zoom in the spacetime, smaller and smaller, at some point you can see that the structure of spacetime drastically changes. It actually fluctuates a lot because of the quantum effects, the strong quantum effects. So in this sense, general relativity is supposed to fail to explain the structure of spacetime at the very small scale. The order is about 10 to the minus 35th meter. So, okay, the quantum spacetime is really small, but how small it is? So compared to a bacteria, the size is of order 10 to the minus 6 meter. So much smaller than smaller than the size of the bacteria. Then what about the atom? So if you think about it, an atom, its size is about 10 to the minus 10th meter. So our quantum state spacetime is really smaller if we compare to the single atom. So I really wish to understand the physics happen at the very short scale, the space-time physics of the space-time. But at this point, you may think that you don't see any point study this kind of weird small space-time. But we have the strong reason to study that. So the research of quantum space-time is very closely tied to understanding how our universe began. So from the observations, we know that our current universe is expanding, precisely speaking, faster and faster. So if you go back in time, at the very beginning, the size of the universe is very small, and its size is about 10 to the minus 35th meter. So this means that the universe sort of started from quantum spacetime. So if you don't know about the quantum spacetime, it means that we don't even know our beginning. So that's the very big issue. So personally, I have another reason to explore the quantum spacetime. My sort of working philosophy is based on John Wheeler's principle of radical conservatism, saying that base research on well-established physical laws, I mean, to be conservative, but push them into the most extreme conceivable domains, be radical. Then one can push the boundary of science somehow. And in this case, in my case, the well-established physical law means general relativity and quantum mechanics, and push these well-established theory into the most extreme conceivable domains. That's a quantum spacetime. So, but then somehow I can push the boundary of science. But actually, the quantum spacetime, that is a spacetime of a very short scale, fluctuates a lot because of the huge quantum effect. So it is extremely hard to handle or investigate such kind of regime. So then what should we do? There are some candidates, but one possibility is to discretize space-time based on a very simple building blocks. So for instance, look at this picture, and if you look at this picture far away, from far away, then you may see that this is sort of pasty Einstein. But if you zoom in, then you can see the structure of Lego block. And actually, this Lego block can control or regularize the tremendously huge quantum fluctuations. More precisely speaking, mathematically precisely speaking, so I discretize the space-time based on some mathematical objects called simplices, like triangle, tetrahedron, and so on. And then I wish to investigate how the quantum space-time looks like at small scales. So I wish to investigate the structure of the space-time at the very short scale. So these nice picture was obtained by Timothy Budd, my friend, and he performed some numerical simulations to obtain this picture. So this is a real result. So actually, many people working on this thing use the computer simulations to investigate the structure of quantum spacetime. But I tried to perform analytic calculations to investigate or to read off the law that governs the quantum spacetime. I think that to get some quantitative results, I need the analytic calculations. That's why I stick to that. But I think that you think it's very hard or too hard to investigate, but it sounds hard, but hard doesn't mean impossible. So I'm trying, but to be honest, it's really hard. So at this moment, I think about a toy model, two-dimensional toy model consisting of one space and one time. And actually, I performed some analytic calculations and obtained some nice results. But actually, I have the higher dimensional models, I mean, a realistic 4-dimensional model in mind. So in the future, I wish to explore by analytic calculations. Okay, I will stop here. Thank you very much.
Thank you very much, Sato-san. So, any questions? If you have a questions, just speak up. For the common, yes, please.
Please.
And personally, just you. And do you believe or do you think ultimately the space-time structure is discrete?
That part I'm not sure, but the philosophy to discretize space-time is that that's regularization. So I introduced some discrete structure to regularize the quantum fluctuation. So in the end of the day, I think I need to remove that couple. So I think well, at this moment I don't know, but it could be. Yes.
Do you expect these quantum fluctuations? Do you expect them to turn into some classical fluctuations at the level that we observe? Like, do you expect randomness in the result?
Yeah. So we observe all kinds of fluctuations across the quantum.
So I'm not familiar with your field. So, and in the figures, what is the meaning of the edges or the vertex or the colors in the figures?
It doesn't mean anything, but just so for instance, look at this one.
Yeah.
So the same color means the same time step. So the different color means the different time. So time flows from here to there.
Time step for the events
Of the universe. Of the universe. But to obtain these figures, I think the color, well, I think the color doesn't mean anything except for these two objects.
So these change over time.
Yes. The shape of the universe changes as time changes.
The ones where you've got the time step, those are really CDT situations, right?
Yeah, exactly. These two. Yes, this is the CDT one, and this is generalized. But this is the simulation for the generalized CDT without wormhole.
I have a relevant question about the observation. You were saying that the tiny microscopic fluctuations, they could have some effects on macroscopic things, which can be observed.
In the end of
Can you elaborate more on how this could happen in this model?
well, that's very difficult thing. So just perform some path integral to taking all kind of quantum fluctuations, large and small, and what we will see is some observable. So it's very hard to tell, but
If there is some amplification mechanism to enhance fluctuations.
amplification mechanism. Yeah, I think so. To organize the large structure.
So do you think the technique, the numerical, for example, numerical technique of this computation similar to the technique in the lattice gauge theory?
Yeah.
In that sense, yeah. So if I were the atomic physicist working on the lattice gauge theory, I could easily work on this program.
Yeah, I think so. Yes. They use the Monte Carlo exploration. Yeah.
Okay, any other questions, comments? How about the Zoom audience? Okay, if not, let's thank the speaker again.